Hello, we are going to continue our discussion of compressible fluid flow in a tube. So let's just quickly see where we left off. Or maybe even just remind ourselves of something before. Okay. So compressible fluid flow in a tube. Again, we have the standard tube that we're looking at, just a cylindrical. Okay, mouse, hello. Mouse sometimes doesn't want to show up. Come on, there we go. So we have a standard tube. We're going to put it horizontally so we're not dealing with gravity. And we will actually look at the ideal fluid. So initially no, but then we need simplifications. And ideal fluid helps us. It's one of the rare cases where you have a nice equation of state that you can work with analytically. And we're going to standard thing, apply the pressure at the ends of the tube and look at the velocity distribution. Now, one thing that we will assume is we will again assume pressure is a function of z, but it's not necessarily going to be a simple linear function anymore. Our z momentum balance that we started with, there was no need to re-derive it. That's something that we've worked on before. So that z momentum balance is the same as in our initial problem in the vertical tube. The only difference is that we don't have the gravity term right here, so we just have this balance part. Now, when I look at the phi z and take a look at what it is, the main difference is now that that divergence part, divergence of velocity, that I used to ignore for incompressible fluid, I cannot ignore anymore. So this shows up here. So we still don't have any other alive velocity other than z. So I actually have dvz dz as the only surviving part of divergence. Okay, so this is actually what divergence term comes down to. And I have these coefficients 2, 3 mu minus kappa in front of it. Now, we know that dvz dz is not going to be 0 in this particular problem because our pressure depends on z. And basically when but one thing that I can put away is this kappa. Again, if I assume ideal fluid, kappa is 0. So ultimately my phi z comes down to, my mouse keeps disappearing. All right, phi z comes down to this term. Now phi rz is the standard expression that we had before, so it comes down to minus mu dvz dr. So now I want to put those in, but I'm just going to look at a couple of more simplifying assumptions that will help me simplify that equation. So one thing is that I have ideal fluid, so P and rho are linked. In particular, P divided by rho is a constant. And I will also assume that rho Vz, note that I have in this term here, I have rho Vz times Vz. So rho Vz part, I will assume that it's approximately constant. So if I have any local expansion, fluid will speed up. And if I have any local compression, fluid is assumed to slow down almost immediately in reaction to that, so that my rho Vz remains constant. Yeah? So let's see, this was 13. Okay, so this is where we then left off, and let's continue. Basically, this in blue is putting the terms that I have. This is phi zz, so this is minus partial phi zz partial z, minus, and this part is 1 over r partial r of phi rz. So this is my momentum balance once I put in all of these terms that I worked on. And let me just get my notes. So let's now continue. Developing this. Okay. So first thing that I will recognize here is that my rho Vz is approximately constant. And I'm going to call it a constant C. So when I do partial derivative of this, I'm going to continue in black. This is minus partial p partial z plus 4/3 mu second order derivative of vz with respect to z. And then I'm going to apply this assumption, so it's a constant minus constant partial vz partial z. And this is plus mu over r partial partial r. I'm going to leave this as is. Okay. Now, second part that I'm going to now start. First, I use this assumption that I made. Second part that I'm going to use is right here. So remember that we derived that dvz dz is minus vz over p partial z. So I'm going to use that in here, and basically I'm going to pair together this term and this term. So what I have is C and then Vz over P dP dz. Okay. Plus 4/3 mu. The rest remains the same. Now I'm gonna now analyze this term a little further. So I have one, this is actually a constant, right? So whatever in this C, remember that I have 1 minus rho Vz times Vz over P. So now I know this is 1 minus rho over p Vz squared. This is actually but a constant because I have ideal gas. And if I have small velocities to begin with, then Vz squared is small. Okay? So this is actually assumed small. Since Vz is small. Now how small? Let's see if we can actually ignore it. I don't know what this constant rho over p is. Maybe it's some super large constant. Well, let's put in some values. So for instance, I'm going to put for rho 1 kilogram over meter cube. And I'm going to put 10 to the 5 pascals. And velocity, a smaller velocity of 10 to the minus 3 meter per second squared. So this is approximately 10 to the minus 11. Even if I put 10 to the minus 2 meter per second, this would still be around 10 to the minus 9. So compared to 1, it's a pretty small value. Note that all of these units basically disappear. So 1 minus 10 to the minus 11 is, well, 1. Okay, fair enough. Now there is another term that I'm kind of desperate. So now when I look at it, what I have left in my equation, I'm going to switch to blue again, or no, black is fine. Minus p minus z plus 4/3 mu z squared plus, I'm going to continue over here, apologize, mu over r ddr rvz is equal to 0. Now, I remember, let's look at whether we can solve this and what the problem might be. I had actually, without this term, this equation I already had, right? Minus dp dz plus mu over r partial r dv dr is equal to 0. That I had in my standard problem. Let's say that would be flowing horizontal tube of incompressible fluid. And that I know how to solve because essentially my pressure is a function of z and everything else here is a function of r, or that's how it used to be in a compressible problem. So it was easy to kind of separate and integrate separately because things were decoupled, r and z coordinates. Now here I have one more dvz dz, okay? So I have more coupling. So my vz essentially is a function of both r and z. And this term basically makes it impossible to solve things analytically. But let's look at the term. Every time you encounter a situation like this, then the practical engineering thing to do is like, okay, well, let's see if we can somehow ignore this term, okay? Well, so what would, if I look at dvz dz, if dvz dz itself, so changes on vz in z directions, are relatively constant or don't change violently, then the second derivative of it is small. Cool, I'll take that. So basically, I'm desperate here to actually make this something I can solve. So I'm going to think about this dvz squared is z squared. And I'm thinking, okay, dvz dz is relatively constant. I can, or doesn't change wildly, so I can actually ignore this part. Okay. So let's do that. So basically, I'm going to state this quite frankly. I'm desperate to simplify equation further. So I'm going to assume dvz dz is approximately constant. So that second order derivative is approximately 0. And then I will get the equation dp dz plus mu over r ddr r dvz dr is equal to 0. Now, scientifically, we do this all the time, okay? And if you remember the words of Richard Feynman at the very introductory lecture, the correct thing to do would be, okay, solve this, find the analytical solution, but then go and find numerical software that has compressible fluid within, and see what difference does this make. Is this term really something I can ignore or not? We didn't make only one, we made a number of assumptions. I'd say the bigger one would be ideal fluid versus real fluid. Okay? So then again, can you program some more complex equation of state, like Peg-Robinson or something like that, and then verify what is this assumption ideal fluid versus non-ideal fluid giving. So again, you will always make these simplifications, and it's a correct thing to do so you can actually see whether you're thinking about the problem correctly and whether you're leaving the key components in. If the simple model works, don't make it any more complex. Okay. So make it as simple as you need it and no simpler. All right, so let's separate the terms. And this is actually regular derivative since p is function of z only and I don't have any r dependence. So basically I can multiply by r over mu Now, if I now integrate with respect to r, so my only dependence on r, this is my only dependence on r in right-hand side. RHS is right-hand side. So I can integrate with respect to r. So I will have that r dvz dr is 1 over mu dp dz r squared over 2 plus c1. So my dvz dr is 1 over mu dp dz r over 2. So I divide by r plus c1 over r. Using same reasoning as before, we can now say what? C1 should be 0, correct? Since my partial, just because fluid is compressible, that doesn't mean that dvz/dr can blow up the middle of the tube, and by implication, shear stresses. So shear stresses should be finite. All right, so this part disappeared, and now I'm going to actually integrate once again. Remember, Bz is a function of both r and z. Now, do I have just a constant here? Or is this constant a little more special? Yeah, so it's a function of z, so it's something that doesn't depend on r. So in that sense,
the only difference between incompressible and compressible. Right.
Well, yeah, and the fact that this could be a little more complex, so it's not like a linear necessarily.
Okay.
Yeah. Okay. Now, good news is that my no-slip boundary condition is still Vz over z is equal to 0 for every z that I have, right? So every z possibly along the tube. So basically that gives me C2 of z, so I can find this function. And it's equal minus over 4 mu dp dz r squared. So all in all, formally, I will have pretty much the same form. So is everybody done? I need to jump to the next page. Okay. Ready? Okay. So formally, I have the same equation as for incompressible fluid, and that is Vz of Rz is minus 1 over 4 mu dp dz r squared minus r squared. So formally, it looks the same as incompressible fluid, but remember dp dz is not necessarily constant. So let's see what could be a little different and when I actually go and integrate and look at the total mass rate. So if I look at the mass rate, so let's now actually see some fluxes for this fluid. So if I do mass rate, it depends on z, and it's my rho of z times volumetric q of z. So it's rho of z times, and I need to integrate over the cross section. What is my area element? Just RDR? D theta. So since I don't really have the, I don't have the integration with respect to z, so I can actually just then leave this as minus rho of z. I can take dp dz out and integrate the rest like we did before, and that will give you overall so this, of course, I now put in here, right? And when I look at the integration, formally it looks the same as in compressible fluid. It actually integrates the same because dp dz depends on z, but it doesn't depend on r, and I'm not integrating over z, so I'm good. Does it make sense? Now, so my mass rate depends on z, and it's minus rho of z dp dz 8 mu. Okay. Now, I actually have to look at some average over the entire tube since this depends on z. So let's actually see what is the average of mass rate over the length of tube. It would be I integrated from 0 to L dz, and I divide by L. So let's do that. What I have here to integrate, the part that depends on z, is this part. What am I going to use here? Equation of state for it. So I'm going to still assume ideal fluid. So my rho of z dp of z dz is, so my rho of z is basically, I know that p over rho is constant and equals some p0 over rho 0. So my rho is then rho 0 over p0 times p. So basically this is equal to rho 0 over p0, p of z, dp of z dz. What can I recognize here? I'm trying to integrate. Is this differential of anything? Square, right here, square. P squared, right? Divided by 2. So this is equal to rho 0 over p0 d dz of p of z squared times 1/2. Then my integration becomes simpler. So when I go back to my w and integrate, so this r to the 4p over 8 mu, that remains the same. And this, when I integrate, is basically just this function at the ends 0 and L divided by L. So what I'm going to have is I'm going to have minus rho 0 over p0 r to the 4 over 8 mu times 1/2 and then p0 squared minus pl squared divided by L. So I have interesting square dependence here. Okay? That is something that does not show for the regular fluid because P0 minus PL over L is a constant. Okay, so this is quite different from incompressible fluid. I'll put this in context for you, just how, even though here I actually have expression, so I got my final expression, right? Now, let's say that I'm actually solving this on a grid, okay? And I'm thinking about sort of a flow through a network of tubes. In that flow through a network of tubes, which is very common in network modeling, basically you take fluxes. In this case, I would take the mass flux, and I would look at a node that has multiple tubes attached to it, okay? And I will say, okay, at steady state, what comes in has to be equal to what comes out, right? And then I will sum up fluxes of this part, right? So P0 and PL being pressures at this central node and any kind of connecting nodes. Okay? And I will sum those up and I will get an equation in those pressures, correct? And let's say that I'm looking for pressures. Now, in incompressible fluid, that equation is linear in pressures. So I go and I solve a system of linear equations for pressures. Cool. In this case, that set of equations is nonlinear. So now suddenly, if you remember your numerical analysis class, you have to do Newton-Raphson for the system of linear equations, and you're solving for multiple at the same time, so it's a larger system, and suddenly you have convergence problems, and you name it, right? Just by this sort of relatively simple change. I have a expression for it, so it must be simple. Well, maybe when I'm actually solving things is not that simple because suddenly I have a nonlinear system of equations. It's still good. I still have a system of equations to solve, and I can simplify my problem, and I have this expression for flux, but just having nonlinearities can actually bite me computationally, right? And I have to have a whole different set of solvers, so it's not just system of linear equations, it's actually now suddenly a system of nonlinear equations. Okay. All right, so just again, so that can be, it's nice to have a closed formula, but that can have implications in any kind of solver. All right. All right, so this basically changes, I'm gonna just say console. We basically now complete the chapter 2, and we are actually, so our examples of shell balances at steady state are over, and we are now actually going to start chapter 3, and that's the chapter where we're actually going to look at the transient behavior or dependence on time as well. So let's just, this is the wrong. So I will still be writing, but let me just introduce a couple of things using slides. Okay. So our next topic is equations of continuity and motion. And this is chapter 3 in BSL. So look at the chapters 3.1 and 3.2. We will skip equations of energy and angular momentum, and we will then look at 3.5, 6, and 7. So this is our plan for chapter 3. So first thing that I'm going to look at, and I'm going to go start writing, but I want this plot because it's much prettier than anything that I can draw. Okay, so we're going to look at it from the slides. But basic idea is that we're going to look at, for any kind of equation of continuity, it's the idea of conservation. Okay? And this idea of conservation will take a look at elements, and you can think about it as that shell that we had. And in a very simple way, I'm going to look at the Cartesian coordinate system first. And I'm going to look at the volumetric change of mass in time in this shell. So with this volume element. And that change, since mass can not be created or destroyed if I don't have any source like reaction or so forth, it's net mass flow through the boundaries of this element. And when I look at this net mass flow, okay, I have to remind myself that what comes into the volume is the stuff that is orthogonal to the boundary. Okay, so basically parallel to the local normal to the boundary. So basically I can, in this particular simple element, I can look at all of the sides. Each side of the cube has a different normal. Okay? And one thing that I have to remind myself, which is why we get those plus minus signs, is that, for instance, this is my delta x or unit vector in x coordinate direction here. So my inward pointing normal is parallel to delta x. And on the opposite side, it's the same except that it has a negative sign attached to it, right? In order to quantify what's entering this flow. So this is what we typically mean by in minus out and so forth when we're actually solving our shell balances. And when I think about flow, this time component is actually going to go through velocity. So what comes into my element is rho times v, where v is velocity of fluid and rho is the density of fluid. So that's what's carried in. Okay. All right, so let's actually, the rest we'll do in writing, because when I write, I'm slower. And that's a good thing. So equation of continuity, chapter. So I have a Cartesian coordinate system. And I have a volume element. See what I mean by bad drawing? So my volume is delta x, delta y, delta z. Okay. So this is my delta x, delta y, delta z. Okay. So basically my rate of mass change within V is rate of mass flowing in minus rate of mass flowing out. So let's look at two opposite sides, and then everything else will be the same. So if I look at this side and this side, okay, this side here has a normal delta x, and this side here has a normal mod minus delta x, and I'm drawing an inward pointing normal. So at my x, I'm gonna change, continue writing this in blue. So for x is equal to x, what's coming in is rho v dot delta x, right? So that's my projection onto the normal. And then I also have to multiply it with the area of the boundary. So I'm assuming this is constant over the entire boundary. Okay. So if I want to integrate over the entire boundary, I have to multiply by area. Is that cool? So basically my area is delta y, delta z. And basically what's coming out is again rho v dot inward pointing normal, which in this case is negative, so that's where this negative minus sign is going to jump out, okay? So this is going to be minus rho v dot delta x. So this is equivalent as saying rho v projected onto inward pointing normal. And since it's oppositely oriented, that's why I'm saying it's coming out and it has this minus sign. Also times delta y, delta z. So this can be interpreted as rho v dot minus delta x. Mm-hmm.
Just a detail, but should it be like delta and then dot rho v? Because I think that the projection of rho v on delta is going to be the delta going first. It has to do with the angle of the dot.
So you mean this dot v?
Yeah.
I normally don't know.
Okay.
But I think angle, I mean, v dot n and n dot v are the same thing. So yeah, it doesn't matter. So this is my x side. So is everything okay here?
So we were just doing the delta x to make sure we capture all the flow coming from directions onto the surface.
Right. So right now I'm dealing with these two sides. Now I'm going to deal with the entire thing. Yeah.
So if you're looking at area, you would do the normal unit vector of that area, vs or something.
Precisely. So what I'm pointing out is that I'm actually integrating over the surface.
Okay.
Okay.
So this is
So I'm integrating rho v dot normal to the surface. And for these two shaded areas, it's actually relatively simple because I'm assuming rho v is constant over that surface and normal is constant too for this part, and then the same here. And I have 6 of these in this simple element. Okay. If I was in a computational software and I had this complex surface is still a bunch of triangles. So I would go triangle by triangle, and each triangle has a normal. Okay? So basically, I would just sum them all up. All right. So now I will just repeat this process for the others as well, huh?
Don't we need evaluated at for these two expressions?
Yes. So this is going to be Vx evaluated at x. And this is at x plus delta x. So it's constant over the side, but it's different on both sides. Okay? So I'm just simply, let me see, I'm going to say contribution, x contribution. So I'm just going to compute it, complete x contribution. Okay. So this is then, this simply projected is rho Vx evaluated at x minus rho Vx evaluated at x plus delta x and times delta y delta z. Okay. So basically now when I sum up this rate of mass change, when I'm going to now sum up all of the contributions. So my rate of mass change, ddt of mass, is this x contribution plus y contribution plus z contribution. In other words, integrate over entire surface of V. So I'm going to have rho Vx. I'm going to shorten my writing immediately, actually. So this is minus rho Vx evaluated at x plus delta xx times delta y delta z. And now I have the equivalent term for y and z. Okay? So it's going to be minus, so when I project rho v onto delta y, it's going to be rho vy evaluated at y and y plus delta y and my area orthogonal to y direction is delta x, delta z, and minus rho bz, z plus delta z, area orthogonal to z direction is delta x, delta y. Now, this is mass of the volume. So this is actually rho, which is assumed cost. Well, no, I'm not going to assume it constant for now. It's rho times volume, which is delta x, delta y, delta z, right? Not going to write it down, but this is just where we're going. So I'm going to delta x, delta y, z is constant that I can divide with. It doesn't change on the location. So when I divide, I'm going to have d rho dt here. Here it's going to be minus rho vx evaluated at the boundaries divided by delta x, right? So when I take a limit of this, when delta x goes to 0, I'm going to get what? Hi. My next meeting is up. My computer wants to tell me. Okay. Now you saw my schedule for the day. Can we move on? Okay. So basically this is going to be derivative with respect to x over rho vx, right? Here I'm going to have a derivative with respect to y, because I'm going to divide by delta y, okay? And same derivative with respect to z. So what's that going to be? ddx of rho vx plus ddy plus ddz of, that is divergence of rho v. Okay? All right, so we're going to finish it next time.
Okay, so if